Hello friend, I am Ghanashyam and welcome to today's lecture. Today we have to discuss about the most interesting topic, that is resistance, inductance and capacitance of the transmission line in the power system protection. Okay, so on this topic is also you have previously studied in the network theory chapter, I think. So this topic is also important to our network theory, our power system also. So let's see about the what is telling about the resistance in transmission line and inductance in transmission line and other capacitance with its own capacitance and conductance. Okay, so the basic purposes of this study of this transmission line network is to transform electrical energy from generating unit to our various location or to the distribution system, which ultimately supplies the load. So let's see. So there are four parameters in the our transmission network. There are four parameters which affects the performance of transmission line as an element of power system. Those are, one is inductance, another one is capacitance, and then resistance, and then conductance. So let me know the basic thing about the inductance and capacitance, resistance and conductance. So what is resistance? Resistance, the property of resistance is to oppose the flow of electric current. So it opposes the flow of electric current, that its unit is ohm. Okay, ohm is the scientist which discovered this resistance. So its unit is ohm. So resistance R is equal to V by I by its Ohm's law. Okay, and its unit is ohm, and it opposes the flow of electric current. Then let's know about the inductance. So what is inductance? Inductance is the element which store the energy in magnetic field. Okay, we store the energy in magnetic field. Its notation is L, but its unit is Henry. Okay, Henry Becquerel, as a scientist who discovered the inductance, that is its unit is Henry, by its name suggests that. Okay, so L is equal to, so if we want to find, let me write here, if we want to find voltage across inductance, BL is equal to L di by dt. Okay, this is the formula, and this inductance store the energy in magnetic field. The structure of inductance is like that, you know. Okay, so let's see about the capacitance. So what is capacitance? Capacitance store the energy in electric field. So a structure of capacitance is like that. We store the energy in electric field. Okay, so Faraday, one scientist that discovered this capacitance. So notation of capacitance is C and its unit is farad, F-A-R-A-D, farad, R-A-D. Then this short conductance. Another one is conductance. Conductance means which conducts the electricity from one point to another point. You have know already, I think. Okay, so short conductance, which is normally due to leakage in the overhead line insulator. So how short conductance is formed? Let's see. Here two overhead conductor are passes through this like this, and this is like it is one phase and it is another phase. So the distance this covered by it acquire a shunt capacitance, and there is ionization of gas. This ionization of gas can cause the leakage of the current from this to this by the use of shunt conductance, that is very negligible, and it also occur in the insulator case. So there are various type of insulator. Let's take pin type insulator like this. Then it act as a capacitor, and there is a small leakage current over here. If very high amount of current will be passed, then there is a leakage current. This leakage current due to small capacitance, and that is called shunt conductance. Okay, let me erase. So it is always neglected in overhead transmission line because of the very negligible na. And the series resistance cause real power. There is a series resistance which is distributed over the transmission line, and this cause the whole power loss in our conductor, overhead conductor. Okay, so it is clear to you. Then going to next, this resistance is very important in transmission to determine the efficiency and economic study. Okay, and then the power transmission capacity of the transmission lies in only governed by the series inductor. So the capacity of the transmission line, remember that the power transmission capacity of the transmission line is only governed by the series inductance, and the parameter are uniformly distributed, but we cannot calculate the uniformly distributed network. We cannot determine, we cannot predict. That's why we have lumped all the distributed network to a lumped resistance, lumped inductance, lumped capacitance. Okay, to determine or to find the actual, that is not actual but approximate. Okay, I think it is clear to you. Okay, and then it complete, I think. Then come to our next slide. Let me erase. Then line resistance. What is line resistance in the power transmission line or overhead transmission line? Let us discuss all the resistance in the transmission line. So it is the main sources of power loss. There is power loss by which formula? Only this formula na, P is equal to I square R. So the effective, there is a effective AC resistance, which is here R, that is equal to average power loss in conductor in watt divided by I square. How it is formed? By this formula only. So P is equal to current passing through that conductor square into resistance of that conductor. So after getting the I in one side and that R in one side, then P, then I square will be come to our denominator side, that is come to our denominator side I square. So R is equal to power divided by I square. So this is our formula, and the unit of resistance is ohm here. So let me erase first. Okay, then I is the RMS current. This I is the here RMS current in the conductor in ampere. Its unit is ampere A. Okay, and ohmic or DC resistance is given by the formula. So it is our DC resistance or DC. So R is equal to rho L by A. We have already studied in the our network theory topic. Okay, so it is not be difficult to you, I think. So RDC is equal to rho L by A. So here rho, what is rho? Rho is the resistivity of the conductor, and its unit is ohm per meter. How ohm per meter will become? Let's see. Ohm per meter. Ohm meter, not ohm per meter, it is ohm meter, because of the R is equal to rho L divided by A. So rho is equal to R into A, and that L is multiplied with this So R is equal to rho into A, and that L will be come to the denominator side, or A divided by L. Then resistance unit is ohm, area unit is meter square, length unit is meter, so meter cancel, and only left part is ohm meter, so the unit is ohm meter. Okay, I think it is clear to you. And this L is the length in meter, this L in meter, and area is the cross sectional area of the conductor, that is in meter square. So one thing I want to tell you that before going to the next slide, make sure you have to screenshot all this slide, so that it is very helpful to you in further study. Okay, so let's take the screenshot. I think you have done. So going to next slide. So here there is a conductor. This conductor are made up of a standard conductor like this. There are many conductor are connected like this manner. This is called a standard conductor 1, conductor 2, conductor 3, conductor 4, conductor 5, like this. Those are the called standard. To maintain the strength and efficiency and power flow, our standard conductor are placed. This standard conductor like ACSR, that is aluminum conductor steel reinforced. There is a steel in the middle portion, steel conductor in the middle portion, and outside conductor are aluminum. Okay, remember that outside conductor are aluminum conductor. So what it is asking, the conductor resistance is affected by three factors. One is frequency, and another one is spiraling, another one is temperature. So frequency will affect the resistance, and the spiraling of the conductor like that. This is the spiraling. This also affect the resistance, and the temperature increase, resistance also increase. This also affect the resistance. So spiraling of the conductor increase by 1% of the resistance. If we have spiral the resistance, spiral our conductor, then the resistance will be increased 1%. From what? From our solid DC resistance. Okay. And the DC standard conductor resistance is greater than the solid conductor resistance. Okay, remember that. And the what is DC resistance? DC resistance RDC is equal to rho L by A. Yes or not? So, and this resistance is very smaller than standard conductor resistance. Okay, and then concentrically standard conductor resistance is increased by 2% than the standard conductor. You also remember this. And the current distribution is not uniform over the conductor when we pass the AC. If we pass the AC in the conductor, this is our conductor, then current distribution is not uniform. In the middle portion, current will be very small. In the outside portion, outside portion like here and here, our current will be maximum. Okay, our current will be maximum. And then current, the degree of non-uniformity is increased in the increase in frequency. Later on we have to see the skin effect, that is called the skin effect. So, and the current density is greater in the surface of the conductor. Current density, that is rho, or J is our current density. This is our symbol, is greater than the surface of the conductor. Like this is our conductor, this is our surface of the conductor. So current density here in this point greater than the middle portion of the conductor. Okay, this cause the AC resistance is somehow higher than the DC resistance, and this effect is called the skin effect. So let's see what is the skin effect. Before going to our skin effect, let us know the temperature. If temperature will be changed, then what is the effect on the line resistance? So for small change, there is small change in temperature, the resistance increase with increase in temperature. So if temperature increase, our resistance will be simultaneously increase. This is our positive effect. So this relationship is here. RT at temperature T resistance is equal to R into R alpha 0 T. So here R is the resistance at temperature 0 degree Celsius, this R, and the alpha 0, this is temperature coefficient at 0 degree Celsius. And the equation, this equation here, this equation can be find the resistance RT2 at temperature T2. At temperature T2, resistance RT2 is equal to, that is, so by dividing this, we also find the T2 resistance. If we want to find the T1, then if we know the resistance of R12 T2, then we can find the resistance of RT1. Okay, I think it is clear to you. So now let's see about the skin effect. What is skin effect in our overhead transmission line? It is not in our body, okay, it is on the transmission line. So let's see, let me erase first. Going to next slide. What is saying about the our skin effect? There is a non-uniform distribution of AC current. So there is a non-uniform distribution of AC current in a conductor surface and skin effect. This is called a skin effect. That means if I am taking here a conductor and passing the AC current here, I am passing AC current here, that is alternating current. Okay, so this is our conductor surface, like this is our conductor surface. So in the surface of the conductor, the flux will be less as compared to middle conductor. Flux will be less as compared to middle conductor, and in middle the flux will be high. The flux will be very high, and due to this there is a inductance effect. So this inductance is directly proportional to flux, so inductance will also be less, and there is inductance will be greater than. So if inductance is greater than, the impedance is also greater, and here impedance is also smaller. By that, if impedance is greater, then current is also high. No, current is very low because of the inversely proportional to. So here current is very high. Okay, by this rule, V is equal to I into R, or I is equal to V by R. So current is inversely proportional to resistance na. So that's why if inductance is low, then impedance is also low. So impedance is low, then our current is high. So this is our non-uniform distribution. That means in surface of the conductor the current will be very high, and in the middle of the conductor the current is very low. So the current density is higher in the surface of the conductor, and this effect occur in AC current, not in DC current. Okay, in this flux inside the conductor is higher than outside. I have seen here. So therefore the current is higher in the surface of the conductor rather than the inside. And we know L is equal to what? Phi divided by I, or L is equal to what? Psi divided by I. So L is directly proportional to phi, L is directly proportional to psi. This psi is flux linkage. Remember that. Flux linkage. Okay. Let me erase. This is our figure. This is our conductor. This is our conductor. Then there is a flux inside the conductor is very high. So that by the previous formula, this formula, I think it is not shown to you. Let me write again this formula. So inductance is direct proportional to flux. So that's why inductance increase with increase in flux, and inductance decrease with flux in the outer side. And that's why if inductance is increased, there is 2 pi fl, the formula of the inductive reactance, that is 2 pi fl, that is also increased. So by increasing 2 pi fl, impedance also increase. This increase in impedance will reduce the current, and this increase in current reduce the, this decrease in impedance reduce increase the current. By this process our current will be on uniform. Okay, so here this loss, this is our disadvantages. What are the disadvantages? I square R loss, this is power loss increase, effective that is refractive is also increase, and the voltage drop also increase, efficiency also decrease, and the voltage regulation decrease. And it is due to our supply frequency increase. If we increase the supply frequency, then our skin effect increase, and if we increase the area, then our skin effect increase. And if we increase the relative permittivity, then our skin effect is also increased. And if we increase the area of conductor, then our in case of SCSR, the skin effect will be decreased. In case of solid, then skin effect will be increased. So we have already used this SCSR conductor for the purposes of transmission line. Then temperature. If we increase the temperature, then our skin effect also increase, because of the resistance increase with the temperature simultaneously. If resistivity is increased, then our skin effect will be decreased. So this is our full process of the skin effect. I think it is clear to you. Take a screenshot, then we will go for the next slide. I think you have done the screenshot. Then come to our proximity effect. If there is a two conductor like that, like A conductor and B conductor, these two conductor are if they are close to each other, then this proximity effect will be occur. So same direction current will be flow in this effect, and those are attraction type and those are repulsion type. So first figure is our attraction type and second figure is our repulsion type proximity effect. So in the outside of the conductor, the flux will be high, and inside of the conductor, in the two close contact conductor, the flux will be less. So by this there is a inductance increase and there is a inductance decrease. So by this impedance will be decreased, current will be increased, and here impedance will be decreased, current will be increased. So it is due to supply frequency increase, then proximity effect increase, relative proximity increase, then proximity effect increase. That means when they are very close to each other, then proximity effect will be increased. If size of the conductor increase, then proximity effect increase. If distance of the conductor increase, the proximity effect increase. This is the whole process of the proximity effect. Are you understand or not? If not understand, then write on the comment section, then I will further elaborate this topic so that you are really clear to this. Okay, let me erase. So take a screenshot. I think you have done. Let's going to our next slide, that is our ferranti effect. So what is ferranti effect saying? That ferranti effect saying that if there is a voltage in the transmission line, this is our sending end voltage and this is our receiving end voltage. So if receiving end voltage is greater than the sending end voltage, then this effect is called the proximity effect. This is our transmission line, over a transmission line. Okay, and this condition is occur only when there is a no load condition and there is a open circuit. If there is open circuit and no load, then our VR, that is receive end voltage, so receive end voltage will be greater than the sending end voltage. So if there is a closed circuit or loaded circuit, then there is not occur in this ferranti effect. And in this no load operation and the open circuit operation, there is a ferranti effect. That means there is a receiving voltage is greater than the sending end voltage. Then this the proximity effect will be occur here. So it occur in the medium and long transmission line, not in the short transmission line. It occur in the medium and long transmission line. Remember that one thing. It cannot occur in the short transmission line. And due to increase in the here receiving end voltage, so up to it increase up to, I think, 5%. It increase up to 5%. Okay, remember that. And this is our mathematical approach. Here one inductance is connected with the parallel with the capacitance, and this is our receiving end voltage, this is our sending end voltage, this is sending end current. So by applying this, our Kirchhoff's voltage law, sending end voltage minus our sending end current with inductive reactance minus sending end current with capacitive reactance is equal to 0. So by applying this, XL is equal to j omega L, or XC is equal to 1 by j omega C is equal to 0 here. Then VS coming to our left hand side and other are taken to our right hand side. So by taking the current, by taking this current in common, we'll get j omega L plus 1 by j omega C. Then by taking this our current in the outside of this left hand side, then we will get Vs divided by this coming to our numerator, a denominator na. So j omega L plus 1 by j omega C will be coming to our denominator, and this j omega L will be neglected. And because of the j omega CL, that is our very low. So due to this, our total formula will be very high, and this is our neglected because of the very low. So only left term is Vs into j omega CL. Okay, so in phasor approach, this is our VR and this is our Vs, and this is our capacitive current, that is 90 degree because of the capacitive effect, which is 90 degree leading from the our receiving end voltage. And by this we will get ICXL and ICR. We have VR is equal to Vs Ix into XL from this figure only. Okay, so Vs, by putting this equation in here, then we will get this one. So VR is equal to Vs 1 plus omega C L all square. So VR is greater than Vs here. Okay, it is clear. So on the later on chapter, we have to discuss about the inductance and other capacitance, and this capacitance is very big chapter, that's why I am not include in this chapter. So for today's, that's it, and thank you for watching. If you like the video, please share to your friend and subscribe my channel and hit the bell icon. Thank you.